Now, going to the talk, this is, as you see, joint work with my colleagues, my colleague Professor Matveljevic and PhD student Gajic. And I think any talk of this type should begin with explanation what is the title. I mean, there is this HP theory, and that's perhaps easier to explain. HP theory is, I think I can speak loudly enough so that without microphone you can hear me. It's a classical topic in analysis, in complex analysis, harmonic analysis, and goes back to Hardy, Littlewood, Rees, Privalov, Goluzin, and others. And then I'll later, in a moment, explain what are these separately alpha-beta harmonic functions in the polydisk, and then we will go on into this. See, this is a classical subject, HP theory. However, after this initial part, which was tightly connected with the theory of Fourier series, it diverged into different directions. And more general domains were considered and more general operators, right? So you can replace the Laplace operator if you consider harmonic Hardy spaces to some more general elliptic operator. And you can consider more general domains as well as in the plane and also in higher dimensions as well. And then starting around 1980, there was a paper by Geller which did not focus specifically on HP spaces of these more general spaces of functions. It was related to the Heisenberg group, but somehow he needed these more general operators. And typically, they're of this form. You have Laplacian on some domain, and then you have perturbation. See, L1 and L2 are first-order differential operators, and this Q alpha beta, that's an operator of order 0. And you see there is just 3 of the papers which relate to this situation. This one, Ahern, Bruna, Cascante, I'm going to refer to it as ABC paper, Ahern, Bruna, Cascante. It was a fairly interesting and deep paper published already in 1996. And I mentioned this paper by Geller, and there was this mathematician Olofsson and his collaborators who worked extensively on such operators and such spaces. I should mention that there are many papers where you have only one parameter with a bit simpler situation. And now the older thing is again related to the Fourier series and multiple Fourier series. In that case, instead of simply harmonic functions, say of Z1 and Z2, meaning X1, Y1, X2, and Y2, so that's what I said, that's the situation when n is equal to 2. And you see the paper in 1939, well, they considered the summability methods for multiple Fourier series and implicitly started to develop theory of, so to say, 2 harmonic functions. Functions of 2 complex variables on the bidisk, harmonic in each of the variables separately. Okay, and then there are new phenomena, because now you don't have a single operator, you have 2 operators. One acts with respect to Z1, and the other one acts with respect to Z2, and naturally then you can generalize to n-dimensional case. Now I'm going just briefly to review the notation that will be used. You see, some proofs are going to go by induction, so you naturally, if you have variable Z, you can split into n minus 1 dimensional part, and the last Zn. There is a normalized measure on the unit torus. And what is convenient, this Z dot W, this is not scalar product. It's just pointwise product. It's convenient notation. And there will be group action on functions, which comes naturally in this work that I'm going to present and to this conference, after all, harmonic analysis. So there is group structure, convolutions will appear. And some more standard notation, multi-index notation. I think I can briefly skip this. There is usual topology on the space of smooth functions on any domain, uniform convergence on compact sets of any derivative of any order, and standard differentiations with respect to z and z bars. All this is fairly standard. And special functions will appear, hypergeometric functions will appear in certain series expansion. Now let's go to the basic object of the study. I want to explain now what is this separately alpha-beta harmonic function in the unit polydisk. Okay, you have fixed dimension n, you have two n-tuples of complex numbers, and then you have n partial differential operators of the second order, all of the same type. These are L, alpha j, beta j, okay? This is a function, okay, this will work, I guess. This is essentially a Laplacian, okay, constant time Laplacian. This is a function, and then you have these first order operators. Alpha j times first order operator times beta j times first order operators, and this is the operator of order 0. Now, as you see, if you think of it as an operator working in dimension 1 in the unit disk, it is certainly uniformly elliptic, right? But it's degenerate near the boundary. It's degenerate near the boundary because this term does not dominate lower order terms, unless both alpha and beta are equal to 0. Then you have essentially the Laplace operator, which is not degenerate near the boundary. So the harmonic case is a special in a certain case, in a certain sense. And now, just as a matter of notation, the space of these functions is denoted by this, and you can have Banach spaces of bounded, separately harmonic functions, and also those which have continuous extension to the boundary. Okay, and now it's easy to see by general theory that such functions are C infinity, even real analytic. And now, overview. Now we have some basic results. When you start building HP theory, for those who are familiar with this classical HP theory, well, you have power series expansions, which is trivial in the classical case. Then you have existence and uniqueness of the Dirichlet problem. And now, immediately I should say, the boundary data are not given on the full topological boundary of the unit polydisk. Okay? This is because we have a system of operators. The boundary data are given on this distinguished boundary, on the torus, which is only a small part of the topological boundary. So there will be a generalization of the standard Poisson kernel. And then after this, there is this basic HP theory which goes in complete analogy with the classical case. Everything that you know about the HP spaces of harmonic functions on the unit disk transfers with proper formulation to this more general situation, which is more general both in terms of dimension, you have system of operators, and in terms of the operators involved. Instead of Laplacian, you have this operator depending on two parameters. And then there are further finer results, so to say. We can consider slice functions, fix a part of the variables, and get a function of the smaller number of variables. And then to get the Fatou type theorems on boundary behavior, then you have to develop a machinery which is related to maximal functions. And so now let's go into more details. Now you need something to start with. So you need some concrete alpha-beta harmonic functions. I mean, if you work with ordinary harmonic functions, then z to the power n or z conjugate to the power n are harmonic, Bayesian building blocks. And the Poisson kernel is standard Poisson kernel is, of course, harmonic. Here you have these functions, which are going to be used in constructing the Poisson kernel for the Dirichlet problem. Now, this is crucial to note. This is important. If you apply here, make this change of variables, u of zeta times z, so you make a rotation, then this commutes with the operators involved. It's a calculation. It just commutes. This does not, it's not true for the dilations. It's not true for dilations. And that makes for some considerable difficulties later on. So you have to notice this. So it's fine with respect to this action of this group, the n-dimensional torus, but not with respect to dilations. So you have this commutativity relation for each of the operators. And now there is a series expansion done in dimension 1 by Klintborg and Olofsson, and that's fairly recent. I think that's 21. And convergence is, of course, the best possible under these circumstances. And now the idea is to somehow to rewrite this series expansion so that it's going to be suitable to multidimensional generalizations. And here we come to this, which is this notation, which is important. See, if you have P and Q, P is n tuple of non-negative integers, Q the same, then it's pure if this product is equal to 0. So think of this. P denotes which powers will be holomorphic powers, and Q denotes what powers will be complex conjugate powers. See, you see Z m plus, Z negative, m minus. This is for any n tuple m of integers. And now these special functions come into play. See, this f is hypergeometric function, and then we have this expansion in dimension 1. Z to the power p, Z conjugate to the q. That's in effect is this sum from 0 to infinity, also sum from minus infinity to 1, which captures complex conjugate parts. Okay, and we have this. And now we can easily generalize this and get this function. Now p and q are not just non-negative integers, but n tuples of integers. And now this is the main theorem on the expansion. Any separately alpha-beta harmonic function in Dn can be developed into this function series, and each of these terms in the sum separately is alpha-beta harmonic function. Now, as time runs fairly fast, I'm going to skip over not only the proof, but skip over the sketch of the proof. Basically, what you do, you develop this u of z into sum of so-called homogeneous parts. And this homogeneity is with respect to this action of the torus on the functions. And then you investigate each of the terms separately. So we'll skip this, except the definition, what is M homogeneous. This is M homogeneous condition. Now I'm going to go over this. This is the development into homogeneous parts, and then each of the homogeneous parts is of this type, and so on and so on. Now, that works for any alpha and beta. Now, to get into deeper parts of the theory, we need conditions on parameters. And these are the conditions. So the real part of alpha j plus real part of beta j is strictly larger than -1 for any j, of course. And alpha j and beta j are not strictly negative integers. Now, it has two consequences. These building blocks, which were introduced earlier, they extend continuously to the closed unit polydisk. That's the first one. And the second one is very important regarding the Poisson kernel, alpha-beta Poisson kernel, which is going to be introduced shortly. This is the kernel. The product, essentially the product of one-dimensional kernels, not surprising because we have product structure of the domain. And this is the fundamental basic estimate. You see, in the classical unit disk and Poisson kernel, this is positive, and this is simply equal to 1. And here you have this generalization, which is also common in general in harmonic analysis. And then we introduce the Poisson transform, basically, of a measure. So this acts on measures and integrable functions. So we can transform a measure which is given on the torus and get this formula. Okay? And what is immediate, whatever measure you plug in, you get alpha-beta harmonic function because the kernel is alpha-beta harmonic. So that's easy. And now you can consider the narrower class of integrable functions, which you can identify with absolutely continuous measures, of course. And now we have this convenient notation. When you fix multi-radius, I should call it, R1, R2, up to Rn, then you can get a function defined on the torus by this formula. Okay? And of course, this is going to help us to define HP spaces, naturally. Now, the formula for the Poisson kernel, it's a product of one-dimensional kernels, which is built from these functions which I mentioned earlier. And this is simply V of, remember, Z dot zeta bar, it's pointwise product. And so there is going to be convolutions on the torus. Explicitly, if U is the Poisson transform of the measure, you have this formula. Okay? So when you restrict to the torus in a certain sense, you get convolution here. And similarly, of course, for the functions. And now then you can apply, of course, the Young's inequality for convolutions and get some HP results, easy part. And now we have this proposition, okay, measures are mapped into space of alpha-beta harmonic functions. And also if you start with an L infinity function on the boundary, you're going to get a bounded function, and the norm is bounded by this constant. And now we go to the Dirichlet problem. One-dimensional Dirichlet problem, it's of course clearly how to formulate it. It's got to be alpha-beta harmonic in the disk and has to take certain continuous boundary values on the boundary, and you have an explicit solution. No surprises at all here. There is a unique solution. And now the problem is to extend it to the multidimensional case. And here you need an auxiliary result to what happens when you fix certain number of variables on the boundary. So you fix these are by modulus equal to 1. The function is separately alpha-beta harmonic, but extends continuously to the closed unit polydisk. Then this function, of course, is going to be separately alpha prime, beta prime harmonic in the disk of dimension, polydisk of dimension k. And then we have these two results, which taken together give existence and uniqueness of the solution to the Dirichlet problem with continuous boundary data. So you can represent function in this class by its boundary values. Okay, and this is the torus. This is distinguished boundary, smaller than the full topological boundary. And then this one is converse, which is also interesting. If you start with continuous boundary data, then this thing is defined on the open unit polydisk, but it does extend continuously to the closure. It's interesting. You prove this by using Stone-Weierstrass theorem on uniform approximation using results on algebras of continuous functions. Now this is the theorem, okay, which summarizes the previous two results. Okay, now there is a local version. If you have continuity only at certain point on the torus, then you will get something that extends continuously to that point. But you need that the function is in L infinity. Now I'm going to skip, because time is obviously running out, just to get to the HP spaces, because that's the point. And these are defined in an obvious way, right? Analogously to the case of classical Hardy space. You have supremum or of multi-radius of these LP norms of functions on the torus. And it's proved that you can, this wider supremum can replace by narrower supremum, where all the radii are equal. And now I'm going to, on this slide, there is summary of the results. And I could say everything that is true in the classical case is true here. So on the, let us look at this line. You have this space, these continuous functions, and then larger space L infinity, then LQ, LP, and then the measures. Here, P is less than Q. And these are isomorphic by this operator of, yes? How many? 3 minutes. Okay, these are isomorphic to these spaces by this P alpha beta operator. And how do you recover if you are given a function here, or here, or here, or here, or here? How do you get it? To get the function defined on the unit torus? Well, you get it either in convergence in a norm, as this multi-radius converges to 1, or weak star convergence in the cases of the space H1, which is isomorphic to the space of measures, and also in the L infinity case. Now, more on slices. This will skip because time is short. Now, what about the Fatou type theorems? Convergence almost everywhere at the points of the n-dimensional torus. Well, the first is to generalize the classical Stolz cone. Just make a product of the cones. But this is the full Stolz cone. Restricted Stolz cone is obtained as a subset of the full Stolz cone by controlling the speed with which these Rj's tend to 0. See? So this is the distance from the boundary in each of the variables separately. You control the relative speed. So this size is controlled. And then the result is, I'm going just to state it. For an integrable function, you have this restricted non-tangential limit is precisely this function f almost everywhere. Restricted means for any a is the size of the cone, how wide open the cone is, and b is a restriction on the quotient 1 minus rj divided by 1 minus rk. And then for singular measures, the same you can get expected result, then it's going to be 0 almost everywhere. And then, now there is all, I'm going to skip everything except a comment that if you improve L1 to LP, P is strictly larger than 1, or to this Zygmunt class L log n minus 1 on the torus, then you can get this without restrictions on the relative size of 1 minus Rj compared to 1 minus Rk. So you get full Stolz cone and this convergence. And finally, I'm going to end with advertisements. So these are my notes, basically, with collaborators, what we should do. So now, certain parts are done. Okay, done. This Zygmunt class, yes. Is it possible to investigate the case P is strictly less than 1? That's an interesting topic. Go beyond critical exponent 1. Then what about the Helder classes? Helder continuity instead of classical continuity. There is Halfalach, Adel Halfalach, and some of his collaborators did this in dimension 1, these things. Okay, the dimension 1, yeah. Then further direction, can we construct the green functions for our system of operators? You want to solve a system of PDs, right? Then you need some compatibility conditions on the data. And I will be finished in a moment. Then it can be done. You can, each of the factors, each disk you can replace by a ball and get polyballs instead of polydisks. Then can we do the theory instead of LP in general context of homogeneous Banach spaces? I guess it's possible. What about the boundary values in the sense of distributions? Yeah. Can we relax? Okay, that's a specific question. And that's it. Then estimates of derivatives in the spirit of Schwarzschild. Atomic decomposition, this is huge. See, a new article, too much for this one. Carlson type embeddings, this is difficult. This is difficult. This part is difficult. Lusin's area function, this is common in classical harmonic case, growth estimates, and so on. And now I think that my time has run out, and I thank you.